My name is Michael Hansen. In this tutorial video, you could call it, I'm going to talk a little bit about how to do photometry in IRAF. As you can see on my screen, I have a little list. I call it a checklist. It's also for my own sake, so I can actually remember what I need to do next, because doing photometry in IRAF is not very complicated. You don't have to do hard equations or do strange setups or something like that, but there's a lot of steps that you need to do, and that can make it a bit hard to figure out how to actually do it. So like everything else in astronomy, and particularly when you want to do scientific or scientific-like observations, especially as an amateur astronomer, there are some prerequisites you are going to need in order to be able to do this. As you can see here, it's on the first topic on my list. So first of all, you need to have a target observation. Well, actually you don't need a target observation, but since the idea is to do photometry on something, then the most interesting idea would be to do photometry on something that you haven't got any data on. Now, I know that when you go over the archives, there's a lot of photometry observations on stars, various places, but so you could ideally find a star or an area on the sky where you actually have photometric data already. But the idea here is that you want to do photometry on something new. I'm going to explain that in a little bit later, so let's just go on the list. You also need reference star observations, and finally you need reference star photometry. Now, I think the last information is a bit redundant, because the meaning of the word reference star means that you actually have already have good photometry data on those stars. Otherwise, they weren't reference stars anyway. And finally, you need some calibration data or calibration files, bias, dark, and flat. If you're using a good professional telescope with cryogenic cooling, then you probably don't need the darks. You only need the bias, the offset frames, but you definitely need flats in any case. I'm going to explain that in a little bit later on. Let's also go over let's save the short list in a little bit, and then let's talk about why we're actually going to do photometry, because you could ask yourself that, and it's a very good question, why do we want to do photometry? Why don't we just take a picture and find some stars and say they're nice? Well, the idea is that as a scientist we want to know something about the sky. So I'm going to show you an image of a field I have. It's an OV star, which means that it's a little it should be a white dwarf in the Botus constellation. Now, as you can see here, I've marked out, this is in the V filter. I'm going to talk about what you actually need specifically, because the prerequisites here was just sort of a short list for what you need. So this is taken in a Johnson standard V filter, and as you can see, the star should be here, and with a little bit of imagination, you can actually see that there might be a star here, but it's quite weak. I was actually surprised as to how weak this star really is. But it should be a variable star, so it's changing its luminosity over time. As you can see here, you might be able to decipher it from the header here. The exposure time was 120 seconds, so 2 minutes, and I thought that that would be enough, but apparently it isn't. But that doesn't keep us from doing photometry, because we have a lot of other stars in this field here that we can do. Do mind you that, and I'm going to go into a little bit more detail. So let's start with the basics. Why do photometry? Well, I guess most of you, especially if you are already interested in astronomy, have heard about magnitudes. Magnitudes of stars, magnitudes of galaxies. Now, in this series here, and I'm definitely, I think I'm definitely going to split these videos up in small segments, because like I said, doing photometry in IRAF is a lengthy process. There's a lot of steps you have to do, and if I had to do all of those steps at once, it would probably be a 2-3 hour video, and I'm not going to record for that long. So I'm going to split it up in I think small, relatively short videos. So this first video here is only going to serve as an introduction and sort of an explanation on what you need in order to do photometry. So if you want to sort of see the all the steps in one sequence of films, then you have to wait until I have uploaded the last video. But in any case, let's talk a little bit about why we want to do photometry and what it really is. So photometry in this sense that we're dealing with here is the idea that by defining stars to have a given magnitude, you can, for example, say that we have defined, I think it's the star Vega that defines our initial magnitude measurements. Then we have also scientifically decided on standard filters. The most known filters are called the Johnson standard filters. There is an extension to the Johnson standard filters that I can't remember the name. But as far as I remember, the Johnson standard filters are BVR. And those filters are receiving light in specific wavelengths. So the thing is that all Johnson standard filters, when they look at the star Vega, within a given exposure time and other considerations, if you take the same exposure time, all those filters will result in the same output, the same intensity of the star. So that is why they are called standard filters. This means that if I have a friend in Australia using Johnson standard filters, taking an image of a star, well, since I live on the northern hemisphere, then Australia might be a bad example, but let's say in the US or Spain or something like that. So if I have a friend there who takes an image of a star using Johnson's standard V filter, for example, and gets a certain magnitude, then if I take an image of the same star using that Johnson standard filter, not in the same exposure time, but just on the same star, then I should get the same magnitude. Of course, the thing is that you need to have reference stars. So what are reference stars? Well, let's put up let's open a new frame here in DS9 and then open one of the references. So let's take this IC 1613, and then let's just take the V filter again. So this is how this observation look in the V filter. And some of those stars here, I haven't marked them out yet. I'm going to do that at a later time. But all those stars you see here, I'm just going to fiddle a little with the scale parameters. So maybe something like, let's do something like this. Let's set it on 500 perhaps. Yeah, that's 200. That's okay. Let's put it there. So all of those stars here, some of them are actually noise, so you're going to you have to disregard those. But many of the stars you see in this filter actually have standard photometry. That means that some scientist has taken an image here using other standard stars and arrived at some given magnitude for the stars he had in this field, and then on and on and so on. So more and more scientists are going to take images of this field here and then sort of distill true reference magnitudes for these stars here, so that other can take an image of these stars here and then use them for magnitudes, reference magnitudes. So the thing is that when you take an image of a target, you would like to have your reference stars roughly in the same area of the sky, so you don't have large shifts in air density, air mass, and also that the seeing is roughly the same. So that's the first thing. So the idea is that we take these stars here, this is also in the V filter, and then we use something called transformation equations that I'm going to go into later on. We use them to get the real photometry on these stars. So the thing is, first we're going to mark out the stars. So we are going to have the IRAF package for photometry to actually find the stars for us and say where are they in relation to the image. And then we're going to use a list I have. You can download that. It's called the Stetson standard field, standard stars or something like that. You can, I think you can arrive at it just by searching for Stetson. Then we're going to do, when we have the stars marked out, we're going to do an initial photometry. We are just going to use an arbitrary 0-point magnitude. So let me just define what 0-point magnitude is. So as you can imagine, when you take an image of a star, you're going to get light, you're going to get photons. The idea in photometry is that, as the name applies, photo and photometry, you're going to measure photons, and that is exactly what we're going to do, what it is we're doing. The reason why we put the V filter or the filters in front is that we are going to make sure that the light that we get from the star in a given opening, you can sort of say, if you imagine the star going all the way from ultraviolet to infrared light, then we are going to sort of take a little snapshot of that vast amount of wavelength and say this is what we call the V filter. And then we're going to measure how many photons do we actually get from this star. So that is why you also need to check the offset. That's the bias, because if you don't do that, you're going to get more photons or less photons than you actually get. If you have a normal CCD, and by normal I mean a consumer grade CCD, sorry, then you also need to do dark subtractions because you have a lot of noise that you want to remove. And finally, you're going to do flat field frames. Now, for many amateur astronomers, particularly those that are doing pretty pictures, as it's called, flats are used in order to make the illumination of the field the same, in order to make the image nicer. Now, what we're going to do when we do photometry is in sort of the same, but here we're going to say we want the chip to be illuminated evenly. That's very important. And then we're going to use that, we're going to divide our dark and bias subtracted FITS file or image file. We're going to divide that by this flat image here, so that we get, if you imagine that your image is sort of a curved surface, right? A concave surface, for example. That's the illumination offset of the optics in the telescope and the CCD itself, because the CCD might not receive the same amount of photons, or register the same amount of photons evenly across the chip. So that's also one of the things. But if you imagine that that is sort of a curved or curved rocket surface in a convex form, then you take the opposite of that form and divide it, and then you get a roughly flat surface. That's the idea. That's what a flat is. But there is a catch here, and I'm going to show you what that is. I'm going to open a new frame. Remember that you're going to divide. So let's go into the calibration and go to flat, and let's take the V again. As you can see, I have two flat frames here. So let's take, this is for, I'm using the eye telescope because I don't have the Johnson standard filters on my own telescope. So let's open this here, and then let's set the scale to this. Here you can see the image, and you can actually see why I wanted you to imagine sort of a convex or concave surface. You have black out here, almost no light, and then you have a lot of light in here in the middle. This is both a result from the optics, but if you sort of looked at the individual pixels, you would see that there's also deviations. So as you can see here in the middle, we have, if you look up here at the value here, we have 25,889.7. I'm just taking a rough point. Sorry, not a rough point, an arbitrary point. Yeah. You can imagine if I take my data and then divide by 25,889.7, I'm going to get a roughly very low number. I'm going to remove a heck of a lot of data. So I'm not interested in that. So what you do is that you either find the mean, or the mode. I'm using the mode of the entire flat frame, and then you divide the flat frame with this number. So I'm going to show you here the result. As you can see, now we have 1 point something, 1 point, and here we have 0.7, 0. If you imagine that I divide by 0.78, I'm going to change my values slightly, not much, but as you can see, I still have the deviations here, and that's what I was actually interested in. So it's very important when you do, I also have a video where I go over all this in IRAF, where you do the standard calibrations. But it's very important when you do this that you don't just divide by the flat frame you can find somewhere else, especially if you download someone else's master flat frame, because you might be missing something very important, and that is you're going to remove a heck of a lot of data. Now, if you're doing nice images, pretty pictures, you couldn't care less about this, because remember, you're dividing, so you're not going to change the image in itself, but we are counting photons, so we are very interested in that the photons we get from a particular star, let's go back again, let's say this star, is actually what we received. We don't want it to be more or less, because then we're going to skew our photometry. So the idea is, if I am going to cook down to a simple sentence what photometry is, that we are taking this reference star here, which we know, which we at this point don't know the photometry on. We're going to get the photometry from this by setting an arbitrary 0-point magnitude, and then we are going to get some magnitude for this star that is most likely wrong. Then we have our reference numbers, the true photometry of this star, and then we have some transformation equations. So we are going to use the true photometry and the transformation equations, and what I have here, this is the instrument magnitude, right? And then we're going to calculate the transformation equations variables, and you're going to see that later on. And then we're going to go back to our target frame, where we also, let's just pick this star here, where we also have photometry. We have instrument magnitudes, and then we're going to use the transformation equations to correct this instrument magnitude to the true magnitude. I don't believe I told you what a 0-point magnitude is. So a 0-point magnitude is defined as the lowest magnitude you can arrive through a given filter and a given instrument at a 1-second exposure. So if you, for example, put your telescope against a given star, a bright star, some object, exposed for 1 second, then the 0-point magnitude defines the lowest magnitude you can hope to gain. So put it another way, you point your telescope at a given position in a star, then you take some exposure for 1 second, and then the lowest star you would find there, you would find data from, photons from, is the 0-point magnitude. I believe that's how it's defined. We're not going to actually use the 0-point magnitude here extensively. We're just going to set it at some value, because what we are doing in photometry here is actually happening in the transformation equations. But I'm going to go over in a later video in some of the steps that what these transformation equations actually do. All right, so let's give you I'm going to give you an example. This is an object called M67 that I worked on at one of my courses at the university, and I actually retraced my steps, because it's sometimes, since I took the course, it's almost 2 years I think, and since there are a lot of steps in photometry, you quite actually quickly forget it. And since I have not done a lot of stellar photometry, actually the only time I did stellar photometry was at that course, it's something that's easy to forget, because like I said, there's a lot of steps. We're going to go over them in more detail. So I'm going to show an example. So here you have 3 different plots. 2 of them are color magnitude plots, and 1 of them are color plots. This is a color magnitude. Now this is only these are only in BVR filters. So these are the 3 Johnson standard filters that we used. We have magnitudes here, as you can see, for example here, and then we have the color here. A color of a star is defined as the subtraction of 2 filters. So the B minus V color is this, and then we also have the V minus R color like this. So here you can see how the stars are related with respect to color and magnitude, and also here, also here, and here you have the color plots. Now I suppose you have already also seen color plots. If not, then you can look up Hertzsprung-Russell diagram, where you can see that they are actually, I think it's color plots they're using to display the stars. So what you do is with this photometry is that you can find, for example, a globular cluster. And globular clusters tend to contain both old stars and new stars. So they both contain blue stars, but they also contain red stars. And then you do photometry on all those stars and then plot them like this. And then you can actually see, I think this is, you can see you have a straight line here. Now it's been a while, so I can't remember what it's called. I think this is called the main series. And then you can see you have sort of a break going into this hook form, or whatever you want to call it. So this is the main series. This is where the stars burn hydrogen, and then they stop burning hydrogen and go to burn helium instead, and so on, depending on how large these stars are. But as they do that, they break off from the main series, and I believe this is an expression of that. This is a B minus V and V minus R. I think the Hertzsprung-Russell diagram is shown in the same example. Now you can also see that we can get error bars. So you can see here that as we, for example, what we would expect, if we look at this is the magnitude here. As we go down in magnitude, our error bars gets larger. We would expect that, because when we go down in magnitude, we receive less light. Whereas in the higher magnitudes up here, which is actually lower, which it's strange, but that's how magnitudes are defined, you see we have almost no errors here, but there are error bars. You can see the same over here. So, and these are typically the more redder stars you can see here. You can see the color red is down here. Alright. So let's go over the more detailed checklist on what it is that we want to do. So, a photometry shortlist, that is the short version of the checklist. The detailed one is down here. The first thing we need to do is find the stars on both target and reference observations. We're going to use a package, or actually the package is called AppFot, Aperture Photometry. There's also a DeoPhot, and actually we're going to use DeoPhot, but the packages in this sense are essentially the same. DeoPhot has some extra features that I'm probably going to show you also, which make it easier to get stars in a crowded field, because as you can see here, let's just use this one. I actually have M13 as a reference, and as you can see, if I open VFilter here, you can see this is actually an example of a crowded field. I'm going to adjust the scale a bit. You can see here it's crowded in here. There's a lot of stars in here. Let's work the scale a little bit more. Now you can see it. So you can see there's a lot of stars in here, right? Now the reason why it's not very good resolution is because I have binned the observation. I'm not particularly interested in getting nice images. I could color combine them so I get a red, green, blue image, but I'm not interested in having nice images of these observations. I'm interested in having good data, so that is why I have binned them, in order to make the pixels larger and then get more. Essentially make the bucket larger, then I can collect more water. I think that's a really good analogy. The bigger the pixels, the more photons I can gather on the sensor. Alright, so we are probably going to use some of the features in DeoFind in here to find stars in crowded fields. We're going to examine the point spread function in order to do that, but I'm going to go into more details on that later on. So when we have found the stars in our observations, we're going to do initial photometry. We're simply just going to set some 0-point magnitude and then get the photometry from that. Now it's completely wrong. We're not going to get the correct photometry, but we're going to get some results. Then we're going to set up our transformation equations, and those are actually the hardest part of it, because there's a lot of setup files and calibration files and so on you need to set up. Essentially it's a big list of things you're going to do, but they have to be in the correct format in order to the photometry program to do it. So we're going to set up the transformation equations. It's this point here, and then we're going to calibrate the transformation equations using the reference photometry and the photometry on our reference stars, the instrumental magnitudes, to get the transformation variables. So we're going to fit the stars that we have from our reference observations to get the correct variables in the transformation equation, and then we're going to invert this or use the transformation variables on the target data. So you can say that we're going to fit some data in order to get the variables, and then we're going to use those variables to get the correct photometry on the target data. So let's quickly go over the detailed. This is what we're going to do in the videos, the coming videos, but I'm just going to go quickly over it. We're going to correct the air mass, and that is because when you do an observation, most packages, also consumer grade, like for example MaxNDL, put in the air mass at in the FITS header. The FITS header is sort of a long list of things that has been done on the FITS file, instrumental information, where the observations were done, the longitude and latitude, how many seconds exposure time, the temperature on the chip, all sorts of useful information are put in the FITS header. So we're going to correct the air mass in the FITS header, because the FITS header air mass is the air mass at the observation start. But what we want is sort of the air mass in the middle, if you will. So we're going to use the exposure time in seconds, and then we're going to use the exposure start time, and then actually the program set air mass is going to use that together with the latitude, I think it is. And that is why we're going to use observatory. I've done this in already, so but we're going to use observatory, the observatory app, or whatever you want to call it, to check that we have the correct observatory set up, which set air mass is going to use in order to get the correct middle air mass. Then we're going to set the DeoFind parameters. I'm first going to show you how to do that manually. There's a lot of parameters, so it's going to take a little bit of time, but the alternative which I'm going to use, which I use all the time actually, is to set up an IRAF script that's going to set up all these things. Now you can make an IRAF script that set up the parameters and then do the find the stars on one image, because we have images in the U filter, the B filter, the V filter, the R filter, and the I filter. We might not going to use all of those filters, depend on how many reference stars we can get in the different observations, but essentially we have those, At least we're going to use BVR. That's the standard Johnson. So we're going to set up the point spread function. You can see I've already found it. We're going to find the sigma offset from the background. I'll also find that it's roughly 15. Then we're going to get the gain and the noise. I use a program called findgain. I can put it out on my web page and then put the link down in the description below. But what you need in order to use findgain, you're going to need two representative flat frames and two representative bias frames. And then you're going to fiddle a little bit around with how much of the frames you're going to use. Ideally you want to use an area where the illumination is roughly the same. And then the findgain is going to calculate the gain and the readout noise for you. Data max is then going to be the full well capacity, that is essentially when is the sensor going to overflow, times the gain, because the gain is giving you electrons per ADU, and then you're going to subtract 5,000 ADUs. So I got 48,580 ADUs, but I might going to set it to 48,000 instead, just to have a whole number. And the full well capacity you can get from the sensor data sheet. Now, two things. The sensor I've used here has what is called an anti-blooming gate. So let's talk about what happens when we don't have an anti-blooming gate. An anti-blooming gate is something that is going to handle overspill. So imagine that you're putting out your buckets in rainwater and then just letting the rain fall down. At some point your bucket is going to be full. Now that is the full well capacity of the bucket. At some point some of the water you have in the bucket is going to spill over into the next bucket, and that is going to spill over to the next bucket. And when you do that, when you see that on a sensor, on a CCD, you're going to see long streaks going up and down on the sensor. That is called blooming. Now you can imagine an anti-blooming gate is sort of an overspill valve that is going to handle this overspill. But, so you can imagine, alright, fine enough, I'm just going to let my sensor go wild. There's a catch though, and that is your sensor has a full well capacity. And if you reach that full well capacity for your star, then you can't do correct photometry. Now, on such an instrument like this, I think this is a 16-bit, 32-bit. All right, but when you look at this, on a given image, let's find one where this might be it. You can see this is, let's do something else. I'm just going to show you that I think I have an image where the sensor is saturated. Let's take this for example. You can see this has already almost reached this, for example, should have reached 65,000 in the middle somewhere. It probably hasn't, but you can get to a point where you let's take one of the raws and see if it's saturated. Let's take, sorry, it was the wrong one. No, let's just take this one, see if this is saturated. Yeah, you can see here it has reached 65,535. I think it should be a 16-bit. It is 16-bit, yes, that's why. So this star here is saturated. That means that you can see on these 2 points you get the same amount This is not true. So essentially this star here is useless as a reference star because you have saturated the chip. Let's check this star down here. This has also reached 60,535, but as you can see, if I move it around, it changes. Now here it doesn't. So this is also useless as a reference star. So while you don't get blooming on such a CCD, you can still overexpose your stars, and then you can't use them. Now you can see this one is definitely different, right? It's only reaching 3,000. Let's take a larger star like this, 9,000. So those stars are useful. Now you're going to exclude that, and that is what you're going to do with this data max here. Data mine is going to set to a negative value. Sometimes it's going to be 3 or 4 times the sigma value here, so probably minus 30 or 60 or something like that. Then we're going to find the stars using DeoFind. We're going to experiment with the threshold to get all the stars, but not get all the noise and streaks and all the other bad things. Then we're going to use the FOT program to get the photometry at the different apertures to find the best aperture. We're actually going to do something else here. Ideally, what you wanted to do, and let me show you what it is. I'm just going to set the video on pause and then I'm going to show you what it is. Alright, back again. So here you can see I have, this is from the course on doing this kind of photometry. You can see I have magnitude plots for different stars at different apertures. So the idea is that you want to find a point where adding more aperture opening essentially won't give you more data, won't give you more magnitude. So let's say if we put it at 5, aperture at 5 pixels, that wouldn't be good, right? You can see that here that we would be missing a lot of data. Putting at 10, well, that would be better because there's not a lot of rise here. Putting it at 15 would be perfect, I would say, because going from 15 to 25 doesn't really change that much. And if you go to lower magnitude, you can see it's almost flat. Let's open the other one like this. Now this is again 3 stars at different magnitudes, but as you can see we're going higher in magnitude, or actually lower, but we're set at 13. I just had to call it something. So, but there's different stars, again 4 stars I think it is, at different magnitudes, and again you can see at aperture of 15 it doesn't really change that much, right? There's some irregularities, but you also have some uncertainties on this. So from here on you can almost make a straight line, right? And the same down here. We're going to do it a little differently because it would take a lot of time. We're simply going to sort of rough our way out of getting a good aperture. Then we get so we're going to skip this step with FOT. We're just going to guesstimate. Then we're going to get the false photometry for all the images, both the reference and the target. Then we're going to move it to an app-FOT directory in order to easily work with it. Then we're going to set up our catalog of standard stars using the make catalog or MK catalog, sorry. And then we're going to make observations file containing standard stars and program stars. It's called MK imsets or make imsets. Then we're going to make an observations file containing pixel offset, star mains, so on, so on, so on. It's called MK ops file. And when we have all these files here, the catalog, the imsets, and the observations file, we're going to make the configuration file and we're going to examine it manually. Particularly, we're going to remove any unused transformations. For example, if we decide not to use the U and the I filter. Then we're going to determine the transformation parameters using fit params. We're going to transform the magnitudes on the target data using either eval fit or invert fit. There's no, I've not found any way to distinguish between these two before you do it. So if you use eval fit and you get really strange magnitudes, then we're going to use invert fit instead, and then we are hopefully going to get good magnitudes. When we have done all those steps here, we can finally do the data analysis, where we, for example, can get the color magnitudes or the color diagrams. Alright, so this was the introduction to stellar photometry in IRAF, and the next video we're going to look at how to correctly set the air mass, set the deofine parameters, and then find the stars. I think that's the steps we're going to do at first, and then depending on the length of the video, we're going to take some more steps. It's probably going to be 3 or 4 videos long, but I hope you can you are patient, and if you find these videos, of course, if you find them useful, perhaps entertaining, I'm not sure, but if you find them informative, if you learn something from them, then please vote them up. If you don't like him, if you think I'm stupid, then do nothing. But if you think that I'm doing it all wrong, if you think there's something wrong, then you can vote it down. But please also put in the comments why you have done it. Well, I think it's all for me. Thank you for seeing and listening, and then see you in the next video, where we're going to try to find the stars in our field. Bye bye.